So it's a pleasure to introduce Professor Feigin, and it's last lecture, third and last lecture on affine and toroidal algebra and integrable systems. Please.
Okay, so last lecture, and I didn't say much, so let me try. What I talked yesterday, if we have, for example, finite dimensional Lie group, or actually infinite dimensional later, and if n is a nilpotent subgroup here, so nilpotent subgroup as a manifold, it is contractible, and so if we are asking about a ring of function on n, this is a polynomial ring, and more interesting things appear if we make a Q deformation of the group. In this case, it will be some non-commutative algebra which is possible to describe. And actually, this algebra, because it is quantum group, and this is function, if we put Q somewhere, that this is function on a group, and we have UQ of the corresponding nilpotent algebra. And it is more or less well known that for generic Q, these two algebras are isomorphic. So we can describe functions on a group as non-commutative algebra using this fact. But suppose we are talking about more complicated case. Suppose we are considering something like currents from C1 to G, or more algebraically, we can take D to G, where this is notation for formal puncture disk. Just very small disk where such origin deleted. Yes, and in a case if G is finite dimensional, by this way, we have affine quantum group, and it also can be deformed. And what I am talking now, suppose G is too complicated for us. Let us considering map to a nilpotent group, and or again more algebraically, it is like this. Again, classically, it is also some manifold, and the serious problem appear only because this is infinite dimensional manifold. But after quantization, we have something like function on here, and it is some way to describe the corresponding algebra. And I wanted to say that shuffle algebra is a rather generic conception, but in some special case we get this. The shuffle construction which I have in mind is following. First of all, here we have for this G and for this N, it is rank. Rank is the dimension of Cartan here. Just to make my notation simpler, suppose rank is 2. Yes, and in this case, but in general case also, the shuffle algebra is given by some version of Cartan matrix, but Cartan matrix now is matrix of functions. So we can take matrix, 2 by 2 matrix, each entry is just some function. Usually these functions, lambda I, G, depending in a ratio, but it is not necessary. In principle, it can be arbitrary functions, just if we construct the algebra. Now what is this? Corresponding algebra E, first of all, because it is rank 2, it is bigraded. It is A, I, G. I is bigger than 0, G is bigger than 0. Yes, and each component, A, I, G, is a space of functions of 2 types of variables. No, two types again, because rank 2. In general, we have more type of variables. And now some conditions. There are several ones, but first, they're symmetric in X's, and they are symmetrics in Y. Now about product. A product is, we have AF from A, I, J, and we have G from A, I prime, and J prime. This shuffle product is function AF, and we have x1, x I plus I prime, y1, yj plus j prime. And what is this? We have to write down f x1, xi, I, no, like this, y1, yj, and g. Here we have x, I1 plus 1, and so on. X, I1 plus I2, and here the same with y. Y, J1 plus 1, and so on. Yes, and then in principle, after that, I want to use same things as I did yesterday, make some symmetrization. But for symmetrization, I use this function lambda, and so first here I write down some expression in lambda. So, for example, here product lambda 1, 1, x alpha, x beta. Alpha from this group, beta from this group. Then I write down lambda 1, 2, x alpha, y beta, and the rule is the same. X from here and y from here. And it is not all, because next term you can easily see we have to write to 1. Yes, and here x. Y group rule is the same. X is no, in this case we take y from this group and x is from this group. And similar story here. And so it is some kind of product of these lambda factors. So we have many of them. And after that, we take symmetrization. By symmetrization, it means that I make symmetrization surely separately in x and separately in y. And after that, it gives me, so yesterday what I had when I described shuffle algebra, I used rank 1 case, it was SL1, and my function was, such kind of function was z1 minus q z2 over z1 minus z2. It was yesterday, now it is more a general construction of such kind. And now let me talk about example. Rank 2, and this is let's take simplest rank 2 case, and this is SL3, and in this case corresponding matrix, the rule is following, that for SL3 Cartan matrix is 2, 2, minus 1, minus 1. And usually if you go to quantum case, you use not in quantum group, you use not precisely this, but this q square, q minus 1, q minus 1. No, usual construction of quantum group is going on by this way. I mean, you fix some matrix, which is just this, and it is just black box, some construction which give you from this UQ of nilpotent for SL3. And it is also surely well known, it is sort of generalization. Now you go from this to this, and then you go to what? You go to z1 minus q square z2, and z1 minus q square z2, but I like also to have denominator, and here you have z1 minus q inverse z2, z1 minus z2, and here is, I think, z2 minus q inverse z1. Z2 minus z1, it is like this. Yes. And then I think I do not make mistake here, but okay, I think it is correct. So what is this? So by this way, we have here, if we use only this, I get subalgebra here. It is the sum of a I0 by I, and it is subalgebra which is isomorphic to what I constructed yesterday. But let me say about this a little bit more precisely. Well, I have this matrix, and then I want to use it to construct the algebra, but the question is, I said that algebra consists in symmetric functions, but let me say this in more exact way. So I want to use this. I want to use this as a product. And so let me start. So first of all, in my algebra, I definitely have 0, 1. And I have 1, 0. And it will be function in one variable, and here in algebra, so it will be C x inverse, and maybe it is 1 here. Suppose better to say y1 inverse, and this is C x1 inverse. Yes, and after that, I generate some algebra so it is some big things if I do not specify what kind of function I use. But now I wanted to say it more precisely, so here I have this, here I have this, and also shuffle, which is corresponding to this matrix, or better to say this matrix, is subalgebra generated by this and this. And the point is now that corresponding subalgebra can be described. So first of all, what kind of function we have? I have function fx1 xn, y1 ym. Yes, but as I explained, this factor, because here the pool of only order 1, then after product it does not produce pools here and pools here. So we expect, and we really have, that in this shuffle algebra corresponding functions are polynomial, Laurent polynomial in x's and y's. But we have these terms and these terms. In this case, we have pool in x and y, and they're surely not canceling. Therefore, the function which we get in my algebra, they have the following structure, xy minus yj. And if I write it by this way, then now f is Laurent polynomial in x's and y, and it is symmetric like this and like this. But the important point is that in such kind of algebra we have some version of Serre relation. Serre relation here means the following, that such kind of polynomial which belong to my algebra, they satisfy so-called real condition. Real condition is means the following. So suppose I am looking what I have in degree 2, 1. No, 2, 1 are polynomials. No, what are they? They will be function in x1, x2, and y. And here I have x1 minus y, and here I have x2 minus y also. But we are looking what we have here. It means what? How we can get here. For example, we can take one part and product to 1 0 part, and then we get something like this, or we can go there by other products. But it is easy to check that in all cases this function will have zeros. And these zeros are organized by the following nice way. Then in this case, function f is 0 if I substitute x1, x2, x3, y such that this ratio x2 over x1 equal q11, and q11 is this. And x2 y2 over x2 is in q21, it is q inverse here, and this is x1, x2, and y1. So here it is, I am talking about this ratio, I1 over x2. And the will condition means also then I have x1 over y1, and if it is q12. So the statement which can be easily proved if you just look into a formula for a product. You look to a formula for a product, and it's many terms. You make symmetrization, but it's easy to see that any term is 0 on after such kind of substitution because of structure of this function lambda. And and the will condition, this is because schematically you write variables like this, and it is q11, it is q12, it is q21, and no, in our case, such kind of it is possible if the product of such q's, this times this is 1. And in our case, it is just this because it is q squared, q inverse, and q inverse. Yes. Now, similar story is happening surely because in our case, x and y are symmetric. If I consider x1, y1, y2, so the similar story about zero condition will be true. And also, I want to say that if you go further, it means calculate product, then the function in general, so if you have x1, x2, xn, y1, and so on, ym, then it is 0 if you take 3 of them, say x1, x2, and y1, and if you organize it by this way and substitute corresponding triple diagonal, then it has to be 0. This is such kind of condition, and in this special case we have x-xy relation and y-y-x relation. And small comment about this, that it is just shuffle things, but if we No, some theorem which in this, at least in this case, it was complicated to prove, but after generalization it is not so easy that if, this algebra depending in parameter q, if q is generic, then algebra generated by this and this shuffle algebra in my definition is just describing by this way. So it consists in functions which are Laurent polynomials with pools and with such kind of zero conditions. And one more comment is that if you write this fact in generators, I mean, you have A1, 0, and this is C x inverse, and suppose xi will be ei first, and similar story from A01. No, maybe yes, it will be first, and here yj will be denoted by j1, j2. And if you take these generators and trying to write down relations, then it satisfies quadratic relation like in the usual quantum group business, and also satisfy some cubic relation, which in standard notation are Serre relations, and in some sense it is equivalent way, but better to say that this algebra is dual to algebra which I describe by generator and relation. It is a usual point, and maybe it is not so important for us now. And but no, this is important definition, and what I want to say that in principle you can construct such things for any Cartan-like matrix. You can use any function, any collection of functions and do something. But no, as usual, Kac-Moody algebra for generic Cartan matrix, it's rather mysterious and complicated object. And we have, no, it is possible to say something, but not much. In this case, situation is similar. So first things, we can use here Cartan matrix for finite dimensional, and go by this way. Or we can use here Cartan matrix for affine and go by this way. For example, we can take affine SLN to start with, to go further, I mean. And the corresponding Binken diagram is like this. Suppose SL3 we have, and SL2 also, but maybe SL3, let me write it by this way. So I have 3 vertices and such kind of structure. And then the corresponding Cartan matrix, it is 2 on the diagonal, and we have -1 here, -1 here, and -1 here. And so 0, 0, no, not 0, everywhere -1 in this case. Yes, and then I do just the same things. So I go to such collection of rational functions, and then I do this. And in this case, it gives me some algebra which consists in function in 3 group of variables because of I have 3 type of colors. Yes, and and this kind of story, what? Here, for example, I had SL3. And then, because I'm going here, then by this way I describe SL3 hat. And corresponding algebra, as I tried to explain, we construct not all SL3 hat, but currents from a circle or from disk to a nilpotent, and this algebra pretend to be and really is the function on the deformed manifold of such kind. And if you are talking here, you are starting from with SL3, and by usual setting you get quantum SL3 or corresponding nilpotent group. But if I go by this way, I construct a toroidal algebra, and it is like this. No, this description of this shuffle, what is this? It is some collection of functions with pools and with relations which are on this language are will condition. And if you no, the natural problem after that, using this language to say something about size of the corresponding object, how to count such kind of polynomials or Laurent, no, for Laurent polynomials we have not conception of a character, but for usual polynomials we can. So it is possible to say what is the size of the corresponding algebra. Unfortunately, I cannot explain something about this. Only what I want to say that in this case, no, it is Cartan matrix, yes, but we also have conception of JL1 double hat, and this is looking not precisely, not is going precisely by this way, but actually it is version of this toroidal algebra. So as usual, here we have SLN, n is bigger, 3 or bigger, it is safe zone. 2 is something special, and 1, what is this? This is the question. But here we can say what is this, and this is most popular algebra of such kind. It is corresponding to 1 by 1 matrix, and the corresponding function is Z1 minus Q1 Z2, Z1 minus Q2 Z2, Z1 minus Q3 Z2, and here we have Z1 minus Z2 cube. Yes, and no, first of all, we can determine the shuffle algebra by this way, because it is only one color. Then which saying that this Q and this Q looks very different, but really not. But it is not my subject now. But I want to say the following. Well, suppose, let us return to the shuffle for SL2, but first with Q equal 1. So in this case, situation is simple. So I have C and function in one variable, then function in two variables, and so on. And this is such functions are just symmetric polynomials, and suppose that this symmetric polynomial here Laurent, and in this case, product is just this shuffle, but with function 1. And so this is my algebra, and this algebra have a collection of factors. First factor, A1, is the following. I consider here factor, it means it is C, here Fx. So I do not factorize here, but I factorize here. The factor will be functions in one variable, here also function in one variable, F1, F2, F3, and so on. And I have map from this to this. And in this case, it is simple. It is just a restriction to diagonal. It is going on x1 equal x2. Here I have f x1, x2, x3, and here it is going to substitute the diagonal x, 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 and therefore I get here some algebra which size of this as polynomials in two variables. It is not precisely so, but algebraically it is not very good, but it is close to what I want. And but it is not a serious point. I cannot be very precise now. Next story is following. That let us consider the part of degree n here. And here it means that I'm talking about function in n variable. What is this? So this is function symmetric, so they are living in C times C times C, maybe C star, if they are Laurent polynomials, factorized by symmetric group. Yes, here we have discriminant divisor. No, discriminant divisor, it means that here is collection of points x1, xn, and divisors is discriminant, so if some xi equal to xj, then such collection of points belong to this divisor, and this divisor surely is, as manifold is rather singular, but it has components. I need a rather rough description of this, a rough decomposition of this divisor. So this divisor is D, and then here we have D1. D1 is what I have there. It is collection of all points are coincide. Then here we have D2. D2 is a collection of x1 and so on xn, such that we have in this set only two different kind of x's. So it means that, for example, x1 equal x2 and so on equal xr, xr plus 1 equal xr plus 2 and so on, and equal xn. So we have two different type of points, and then it is D2. And so D3 is a collection of points where only three different ones, and so on. After I make up such a definition, I can describe my next quotient. So so I have such kind of divisor D2, for example, here. No, D2 here is all things, here is all things, but still let me write down like this. It is CD2 here, but it is the same. CD2 here, but it is all space of function. Here we have C D2, and in this case, they are just function on this discriminant divisor, and we have a map from this to this, and similar story appear. We have four variables and so on. Yes, and no, D2, D2, D2 here, same notation, but they are living in different spaces. Yes, so I have C here, and then I write, it is like this. Next, and this is what I call A2. And next it will be A3. Again, it is C, and this is C. D3 plus, and so on. And so such algebras are a real quotient of this, and I want to say that no, anyway, we have, by this way, we get some graded commutative algebra, and this algebra are function on something. And these something are not precisely, but very close to what we're calling Zastava manifolds. For SL2. No, first, they're close, not precisely. If we want to make it more precisely, then we have to correct what we have here. All, but no, because if you have spectrum of this manifold, just as I said, it is not very good. But it is close to what I really need. Yes, and let me explain what is this geometrically. I said that I have SL2 hat, for example, and it is affine Grassmannian there. So it is affine Grassmannian, and it is fixed point here. Then I take currents to a nilpotent, and here I act to this point by nilpotent manifold, and then closure of this, it is some manifold infinite dimensional, which I discussed yesterday. But this manifold can be decomposed in the terms of cells. So for example, in this manifold, I have just orbit of this. It is some infinite dimensional manifold, but my manifold is compactification. So it is some collection of strata, actually. And now usual definition of Zastava is more or less following. In such manifold, so skip some details. In this manifold, we can take some strata, which numerated by L, and let us take the transversal slice for that. And this transversal slice is some manifold, and I pretend that surely after some small correction, function of this can be described by this way. And now, no, geometry is geometry, but we are talking about some kind of algebra. And the approach or just question. You have some collection of manifolds which are Zastava-like, suppose, and they depending in number n. So n is this. So so this is big things, and I factorize it. It will be a function on D1, function on D2, function on D3, and so on. This number play a role of topological number. And then a usual approach in this instanton counting is following, that we have the collection of manifolds which are more or less spectrum of corresponding algebra. It will be some manifolds, M1, M2, M3, and so on, and M0 also. Yes, and what I described here are just functions on 1, M2, and so on. And these functions are bigraded space. It is because two-dimensional torus are acting here. So I can write down the sum of y times n character of space of this function. It will be some series in principle, and maybe in Z is some q, but here mn. No, this object is calling the statistical sum, and some expectation this, if you play this game, you get something interesting in a sense that the corresponding object have many properties, and I do not know physical arguments. No, I know, but I cannot repeat physical arguments why such kind of construction give you usually the object which satisfy difference equation in principle in all letters which we have here. So here y is counting, instanton counting, z here is equivalent parameter, and corresponding things satisfy difference equation in z and difference equation in y. And what I said, that if you write down this and calculate character in this case, you get more or less what I call Toda, but with different powers. So my formula was yn qn divided to some finite product here. Different construction here change q factor here. It can be n square, for example. But in all cases, such kind of things satisfy some difference equations. So No, the point is that we cannot spoil by a simple way the fact that we get difference equations. Yes, and no, my time I think is almost gone, but what I want to say. First, if you are talking not about this, but about deformed case. About deformed case, the point is that now we have non-commutative algebras. Yes, but with some special choice of functions. And about discriminant divisor, this is still similar because, for example, first step, again, in this shuffle we still have symmetric functions, but substitution now will be different. I have to take function f x1, x2, xn, and then I go to fx, qx, q square x, and so on, qn minus 1x. And it will be correct way to do it. No, and discriminant divisor after that, for example, D2, it is similar story. We have collection of x's such we can divide it into groups, and these two groups are organized by this way. And so I can restrict, and it gives me a quotient, and it gives me some kind of algebra. Yes, and no, about the difference equation and so on, it is a lot of information. I want to say that no, surely you can, so if, no, first about generalization. Well, generalization is if you have rank 2. So what to do? No, geometrically, again, we have transversal slice of something, but it is some construction which pretends to describe function on it. But what to do? Simplest possibility is following. Rank 2, it means I have function in x1, xn, y1, ym. Yes, and no, with some properties. But again, I have to consider some function r and s. And I substitute in x's and substitute in y's, more or less by the same way as I did for SL2. For example, if it is 1, 1, I'm finished in a moment. I restricted 1x, x, x, and y, y, y. And similar story I can do. No, substitution is does not deal with a specific structure of function lambda and so on. I make up this SL2 business along each route. Therefore, I get a collection of commutative rings or non-commutative if I am talking in deformed case, depending in R and S. And what I have to do after that, I have take summation y1 R, y2 S, and here will be a character of corresponding things, and this is the object which satisfies some higher order things. So again, this is how it is going on, and unfortunately or fortunately, I have to stop.
What? The word Gastava, it's a Russian word. Yeah?
Russian, Maybe Mirkovich invented it. I think so.
It means in English outpost.
I know. And in Croatian language, maybe it means flag.
Flag?
Flag, or something like that. But as Russian people, we understand it as you are saying, yes.
Any other
No,
questions?
it is good to have such kind of name. We can enjoy.